Hello, I'm Sean, currently a PhD student at Australian National University. I will be presenting our paper titled, View Consistent Purification for Accurate Cross-View Localization, a collaborative effort involving Australian National University and Ford Motor Company. Firstly, I will discuss the task setting. Our fine-grained self-localization approach employs a flexible number of onboard cameras and satellite images. Additionally, a coarse initial pose is provided through GPS. The chart gives an instance where 4 onboard cameras, front, rear, left, and right, are utilized. The field of view of these cameras is depicted in red along with the initial pose. We aim to estimate the accurate vehicle pose, indicated by the green color. Next, I will explain the motivation of our paper. Existing cross-view localization methods struggle with noise sources and encounter challenges in achieving precise localization. Due to the diverse capture times of satellite images, noise includes moving objects, seasonal changes, and temporal variations. Our approach builds upon the SIBCL method, a lidar and visual hybrid sensor solution. Our method eliminates the necessity for lidar points and instead establishes correspondence through the detection of key points on the ground. We further introduce 3 novel modules. Firstly, the spatially aware feature and confidence extractor, which takes the form of a U-net architecture. Its purpose is to extract features in 2 attention maps, one for view consistency and another for on-ground confidence. Additionally, it incorporates a novel spatial embedding that leverages camera intrinsic and extrinsic parameters to encode precise spatial information. This embedding significantly enhances localization accuracy. This chart illustrates the embedded spatial information. Heading is embedded using the cosine of vehicle heading angle. Distance is embedded as normalized on ground distance. Height is normalized on the down axis of the ground view, and set to a minimal value of the satellite view. The second innovation is the view consistent on-ground keypoint detector. Its objective is to identify on-ground key points within ground view images. Here is the pipeline of view consistent on-ground keypoint detector. It begins with confidence map fusion, in which all level confidence maps from the view consistent and on-ground maps are combined to create a single map. This figure provides an example of view-consistent, on-ground and fused confidence maps. The view-consistent confidence map assigns elevated confidence to objects that exhibit consistent presence in both ground view and satellite images. Examples include road markings, curbs, and building roofs. In contrast, the confidence map attributes lower confidence to objects that display temporal inconsistency, such as vehicles. The on-ground confidence map focuses exclusively on on-ground cues, such as road markings and curbs. The fused confidence map highlights objects that are both view-consistent and on-ground. To offer a more comprehensive demonstration of the confidence map's capability in identifying ground-level key points, we present a continuous fused confidence map video. Following the fusion of confidence maps, we proceed to detect 2D key points from the fused confidence map. The top part of the image is ignored to concentrate on the ground plane. Moreover, a max pooling technique is employed to avoid overly crowded keypoint detection. This figure illustrates the keypoint detection step. Finally, based on the assumption that all detected points are on the ground, their 3D ground query coordinates are calculated. The key points are subsequently projected onto the satellite view to establish correspondence features and point confidence, which are then employed for calculating residue and point weight. We demonstrate the process of pose estimation in the video. The estimated pose is iteratively refined from the initial pose towards the ground truth pose. We assess our approach using 2 datasets, KITTI and Ford Multi-AV seasonal datasets. Results on the KIT-TI-CVL dataset demonstrate our method's ability to generalize to uncharted routes, using only a front-facing camera. While our method significantly reduces translation error, it exhibits slightly lower orientation accuracy compared to the lidar-based method but remains competitive with the state-of-the-art visual-only method. On the Ford AV-CVL dataset, we evaluate our method's performance under varying lighting and seasonal conditions, employing front-facing camera, 2-camera, and 4-camera setups. Additionally, in log 4 to 5, we analyze our method's generalization to an unseen route. In all instances, our method outperforms existing state-of-the-art methods by a considerable margin. Thank you for listening.